Hey, I'm Michael Sigmund, and this is Lab 2, Lines of Charge, for Professor Berger's Physics 2112 class. The goal of this lab is to determine how two charged tapes interact with each other when divided into different segments, each treated as point charges. These are the fundamental principles we'll need for this lab. And the first one is Coulomb's law, which the electric force equals the K constant times the charge of the first object times the charge of the second object divided by r squared. We'll also need to know about superposition, which is that all the charges added together equals the total charge. And then finally, Newton's second law, which is force equals mass times acceleration. These are the assumptions that we make for the lab. First is that the tape can be divided into different pieces with the same net charge. The second one is that each piece is a point charge. The third one is the charges of each piece add up to the total charge of the entire tape. And then the final one is that we can ignore air resistance. So this is part 1 of the experiment. So the masses of the tape was about 1 gram, and the length of the tape was 0.2 meters. So for the first trial, the distance between the two tapes was 0.03 meters. The second trial was 0.038 meters, and the final trial it was 0.035 meters, which gave it an average distance of about 0.035 meters. So this is the second part of the lab where I find the charge Q of the tape. So first I find the gravitational force, which is mass times the gravity, which equals 9.81 times 10 to the negative 4 newtons. And then I find the charge of this tape by setting the force of gravity equal to the electric force, which is Coulomb's law. And I just rearrange the equation to where it equals T, which is equals Q, and Q is the square root of mass times gravity times the K constant times the distance squared, and that gives Q to be about 1.2 times 10 to the negative 8 coulombs. So this is the code that I made for the lab. And first you can see that I put in the different variables for the tapes, so the distance, the length, the mass, and the charge. And then I find R by subtracting the observed location from the charged particle position. And then took the magnitude of that and then divided R by the magnitude to find R hat. And then I plug that into the electric force equation, and so I got the electric force. And then I just used a for loop that goes through each position of the tapes and then finds their charge and then adds them all together. So when that code is ran, you can see that there are the two tapes and they're each segmented into different sections. And then you have the gravity vector, or energy vector, which is the yellow arrow pointing down, and the electric force vector, which is the orange one pointing up. And each of the purple arrows is the electric force on that specific segment of the piece of tape, and then they all add up to the orange vector. The what if question asked, what if we had modeled our tapes as a single point charge instead of a line charge? And so for the line charge, I got 1.2 times 10 to the negative 8 coulombs, and for point charge, I got 1.98 times 10 to the negative 8 coulombs. And this is due to the fact that whenever you just take it as a single point charge, it's just measuring straight up in the y direction. But if you measure with the line charges, then it takes into account the x direction of the force too. So that's why the single point charge is so much greater and is also much more inaccurate. Finally, the why question, which is why do those estimates differ? And that's because whenever you use the whole tape as a point charge, it will be less accurate than if you find the charge of every piece of tape on the tape using superposition. And the one that will be more close to the real value is if you segment it into different parts.